In this video, we want to look at conservation of mechanical energy. Now that we've studied kinetic energy and potential energy, we want to see how these work together in a conservation law. Just like the conservation of momentum that we did in the previous chapter, we're now going to look at conservation of mechanical energy, meaning that the total mechanical energy of the system is constant throughout the problem that we are looking at. So mechanical energy is the total of kinetic and gravitational potential. So if we take the kinetic energy and potential energy and add them together, and there's no outside forces on the system other than gravity, the kinetic and potential energy sum, the mechanical energy, will be constant. So we could write that equation, mechanical energy final equals mechanical energy initial. But most of the time, we want to write that out in a little bit longer form. Potential energy final plus kinetic energy final equals potential energy initial plus kinetic energy initial. It doesn't matter which side's final and initial. And if we then take those formulas and do the formula for potential energy, mgh, the formula for kinetic energy, 1/2 mv squared, we can write out the formula 1/2 mvi squared plus mghi equals 1/2 mv final squared plus mgh final. So any change that's happening to potential energy, the opposite change is happening to kinetic energy. They are inversely related. So as one decreases, the other increases, and we can use that to find heights, velocities, and a lot of different things with conservation problems. In this first video, we're going to look at some more basic conservation problems, and then we'll have a second video to look at more complicated and multi-step conservation problems. A 50-kilogram block is dropped from a height of 8 meters. How fast is it going when it hits the ground? So we have 1/2 mv initial squared plus mgh initial equals 1/2 mv final squared plus mgh final. Start plugging in our values. 1/2, 50, it's being dropped, so the initial velocity is 0. 50 times 9.81 times 8 equals 1/2 50 v final squared, that's what we're solving for, plus 50 times 9.81, at the ground the height will be 0. So this whole side becomes 0. Multiply 50 by 9.81 times 8, you get 3,924 equals 1/2 50 v final squared plus 0. So 1/2 of 50, this is 25, so I'm going to divide both sides by 25. I get 156.96 equals v final squared, and then I need to take the square root of that. I get 12.5. So the final velocity here would be 12.5 meters per second. Now we actually solved a problem very much like this when we were back looking at free fall, and you could do that using acceleration, using the height and the distance formulas, but this is another way using conservation of energy. Second problem, I'd like you to try this problem on your own and then come back and see my explanation after pressing pause, doing the problem, and then pressing play again. A 1 kilogram ball rolling at 2 meters per second at the top of a 6 meter high hill. How fast will it be going when it reaches the bottom of the hill? So 1/2 mv initial squared plus mgh initial equals 1/2 mv final squared plus mgh final. So 1/2, 1 times 2 squared plus 1 times 9.81 times 6 equals 1/2 times 1 times v final squared plus 1 times 9.81 times 0. So 1/2 of 1 is 1/2 times 2 squared, which is 4, so this comes out to 2. 9.81 times 6 comes out to 58.86. 1/2 of 1 is 1/2, v final squared plus 0. So we get 60.86 equals half V final squared. Divide by a half. We get 121.72 equals V final squared. Take the square root. We get 11.03 meters per second. Now, we have the same ball. How fast is it going? Rolls up a 4-meter tall hill. At this point, you could start with either the final velocity here of 11.03 as your initial velocity and your height starting at 0, or you can start with the original data since momentum, or energy is conserved. Sorry, energy, not momentum. So I'm going to start with the original data. 1/2 mv initial squared plus mg h initial equals 1/2 mv final squared plus mg h final. So 1/2, 1 times 2 squared plus 1 times 9.81 times 6 equals 1/2, 1 v final squared plus 1 times 9.81 times 4. I know that this ends up as 60.86 from the previous problem equals half v final squared plus 39.24. So the first thing I have to do is subtract 39.24 from both sides. You get 21.62 equals half v final squared. Then divide by a half. You get 43.24 equals v final squared. And then take the square root of that. 6.58 meters per second. So previously it was 11. Now it's going to be a lower velocity because it has more potential energy, so less kinetic energy. 2,000 kilogram car traveling at 40 meters per second coasts up a hill. How far up the hill will it travel? So same setup here. So 1/2 2,000 times 40 squared. 2,000 times 9.81 times 0 is half 2,000. At the highest point, its velocity will be 0 plus 2,000 times 9.81 times h final. So 40 squared times 2,000 times 1/2 is 160,000. So 1.6 million. Equals 19620 times h final. Divide both sides by 19620. We get final height 81.5 meters. Okay, that completes some examples of some basic conservation of energy problems. The total energy is conserved as long as we do not have any outside forces or influences on the system. In the next video, we'll look at cases that involve multiple steps, take this a step further, or cases where we're not given the mass.